Welcome to the Explainer. So, you know that incredibly frustrating moment when you're talking to an AI, and 5 minutes in, it just completely forgets everything you just said? Yeah, we've all been there. Today, we're going to unpack exactly why basic vector storage is failing so hard in complex agentic workflows, and how biologically inspired memory architectures are finally stepping in to fix it. If you want to know how we're actually getting to truly autonomous AI, you are in the exact right place.
Here's our roadmap for today. We're going to hit 1. Why basic memory fails. 2. The 4 memory types. 3. Hierarchical memory systems. 4. Active dreaming and consolidation. And finally, 5. The art of strategic forgetting. We're going to trace this whole evolution right from the catastrophic failures of early amnesic AI to the cognitive blueprints that are powering lifelong learning today.
All right, part 1. Why basic memory fails. To get where we're going, we first need to poke at a major pain point. Why standard retrieval augmented generation, or RAG, is just hitting a wall in production.
Look, traditional automation, it's basically a conveyor belt, fixed, predictable rules. But true agentic workflows, they require continuous self-correcting reasoning through highly ambiguous goals. We're talking about advanced architectures like ReAct, where an agent literally has to bounce back and forth between reasoning about a problem and taking an action to solve it. Or think about plan and execute models that map out a huge multi-step strategy before they even make a move. An agent absolutely cannot execute a complex tree of thoughts exploring multiple problem-solving paths at the same time if it just loses its train of thought halfway through. It's a disaster.
The harsh reality is that flat vector databases just break down at scale, and it happens in 4 specific ways. First, context poisoning. This is when hallucinated errors get saved and then treated as hard facts in future loops. Then you have context distraction, which is basically trying to find a needle in a haystack of irrelevant noise. Third is context clash, where the system loads outright contradictory facts into the exact same window, which completely paralyzes the AI's logic. And finally, work duplication. This one literally burns expensive tokens because agents in a multi-agent system don't realize someone else already solved the problem. It is a massive, massive bottleneck.
Moving on to part 2, the 4 memory types. To fix these bottlenecks, researchers are doing something pretty brilliant. They're looking directly in our own brains, mapping human biological memory right onto AI architectures. First up, working memory. Think of this exactly like your laptop's RAM. It's bounded by the LLM's token constraints, and it requires active, constant maintenance. When an agent is doing chain-of-thought reasoning, thinking out loud, breaking a problem down step by step, all of those intermediate logical steps, they live right here in the active workspace before they just vanish when the interaction is over.
Next is episodic memory. This is basically the what happened and when tracker. It records specific past experiences and, crucially, keeps the temporal sequence intact. This is what lets an agent maintain perfect continuity across totally different sessions. Imagine a customer support bot that actually remembers it processed your exact refund requests 3 weeks ago and just seamlessly picks up the chat right where you left off. That's episodic memory. It adapts to returning users without starting from zero.
Then there's semantic memory. So if episodic memory is I went to Paris last year, semantic memory is just knowing the fundamental fact that Paris is the capital of France. It doesn't track what happened, it tracks what is fundamentally true. It's a persistent knowledge base, usually built on heavy-duty vector databases or knowledge graphs, making sure the agent operates on a rock-solid foundation of facts. And finally, procedural memory. This right here is the true automation engine. It encodes learned skills and complex action sequences. Think about toolformer concepts, where an AI teaches itself how to use an external API, or OpenAI tool calling. Procedural memory lets agents execute those validated workflows on autopilot. Once it learns the exact procedure for a multi-step planning loop, like securely authenticating a user, hitting a live database, and drafting a report, it just does it. No need to burn tokens reasoning through the same steps over and over.
All right, part 3, hierarchical memory systems. So how do we actually route all this information efficiently when our databases inevitably swell to millions of entries? Because flat storage, absolutely not going to cut it anymore.
Enter the OS-inspired memory OS architecture. This shows how advanced agents use explicit memory management functions to literally page information between short, mid, and long-term storage tiers. Think of it as a router-based system. Instead of frantically tearing your entire house apart looking for your keys every single morning, the router just intelligently directs the agent to check the one specific drawer they're always in. It is highly targeted, and it achieves massive token savings while keeping the context window incredibly sharp.
So instead of scanning a flat database top to bottom, these systems route queries layer by hierarchical layer.
The domain layer identifies the broad area, like customer support. Then the category layer narrows it down to shipping issues. The memory trace finds the relevant thread, and finally, the episode grabs the exact time-stamped message. It is surgical. It drastically cuts computational waste and slices latency right down in production.
We see this play out perfectly with frameworks using note construction templates. By using the LLM to actively generate keywords, rich context, and categorical tags the moment it stores something, the memory system shows true agency. It's actually evolving its own contextual connections, kind of like a Zettelkasten, building a highly linked web of notes, rather than just lazily dumping data into a bucket and praying it can find it later.
Number 4. Active dreaming and consolidation. This is where it gets wild, drawing straight from human biology. Because yes, autonomous AI agents actually need to sleep too.
Here's how an agent actually learns overnight during downtime. It uses a reflection-style architecture, meaning it explicitly critiques its own past actions so it doesn't repeat mistakes. It clusters its historical execution failures, abstracts a brand new generalized rule, and then literally generates a synthetic, counterfactual dream scenario to test it out. It actively verifies the solution using self-consistency checks, basically asking itself the same question multiple ways to make sure it always gets the correct answer before confidently locking it into long-term memory.
By pushing data through this active dreaming consolidation pipeline, an agentic memory system actively verifies its own synthesized knowledge. Unlike basic models that frustratingly start completely fresh every single session, this guarantees lifelong learning without catastrophic forgetting. It seamlessly translates raw, messy, episodic memories into rock-solid procedural and semantic rules. And finally, Part 5, the art of strategic forgetting. This brings us to the absolute most counterintuitive requirement for a highly intelligent system, the ability to selectively forget. You're probably thinking, why on earth would I want my smart AI to forget anything? Well, unbounded infinite memory is actually a trap. It leads straight to context distraction. Millions of low-value, outdated entries just dilute your retrieval quality, they inflate your token expenses, and they burn right through your compute budget. Storing absolutely everything is, frankly, a massive design flaw. To fix this memory bloat, developers use the RIF formula. It brilliantly mimics the human Ebbinghaus forgetting curve, the psychology of how we naturally forget over time by scoring memory based on recency, relevance, and frequency. It's sophisticated math that lets the system strategically score and prune the noise, ensuring the AI's limited context window is filled with nothing but high-signal, highly relevant data.
So, as we wrap up this explainer, I want you to ask yourself, is your enterprise AI currently drowning in its own disorganized data? Or is it equipped with the cognitive blueprint to forget the noise, run complex ReAct loops, and multi-step planning and act solely on what truly matters? Thanks for joining me on this deep dive into the fascinating mind of the modern AI agent. Catch you next time.